In this podcast, we're going to talk about heat transfer, okay, a little more in depth. All right, so there are three different ways that chemical systems can change energy. Heating and cooling is one of them. Phase transitions, so going from one state to another, and then through chemical reactions. So we're going to study these three things, and because they are three different ways that a system can undergo a change in energy, there will also be three different ways to solve them. Okay? All right, first let's just talk about heating and cooling, and we're going to talk about specifically water. Okay, so let's first talk about what's happening at each portion of the graph. So first I'll just give you a little background on the graph. So you have an increase in temperature at the bottom on 1, and then on section 2 you have no change in temperature, and then 3 there's another change in temperature from 0 to 100, and then 4 again no change in temperature, and then 5 another change in temperature. At these sections where there's no change in temperature, energy is still being added. Okay, so that's something that's good to keep in mind. All right, now this is a great little animation of what's going on during a heating curve. So first you have ice warming up from 15 to 0. So this is solid down here that's heating up. Then you have another flat line, the first flat line. That's going to be a phase change. This is a phase change between solid and liquid. So at this point, you have a change of state. Then again, you have increase in temperature. This is liquid water that is being warmed up. And then again, you have a no change in temperature on another flat line. That's another phase change from liquid to gas. And then lastly, you have only gas, and now it's just being heated. Okay, so that is what you have at each portion. All right, here's a different way to look at it. If you just ignore the little weird letters and just focus on the states and the molecular level, you see that at first we have a solid. They're all very ordered, very compact. First flat line, you have a transition between the solid state and then going to liquid. The big diagonal line, you have all liquid that is being heated up, so they can slide past one another at this point, the molecules. And then you have another transition, so now we have some liquid going to gas. And then lastly, you have just gas. All right, so when a substance melts, boils, or is warmed up, the energy is being absorbed or gained. So we're talking about going from solid to liquid to gas and even to plasma. Okay, so going up, you are absorbing energy to go from a lower state to a higher state. Remember, these all have low energy, and these all have higher energy up here, so it increases going this way. So you have to get more energy. These are endothermic processes because you are adding extra energy. Now, if a substance condenses, freezes, or cools down, the energy is released or lost. So going from liquid to solid, or gas to liquid, or plasma to gas, okay, you are going from high energy to low energy, okay? So you're going to have excess energy when you're making these transitions, and you're going to release it. And that is an exothermic process. All right, so specific heat capacity is something that we're going to utilize to help us determine what's going on particular portions of the graph. All right, so specific heat is basically the amount of energy needed to heat 1 gram of a substance by 1 degree Celsius. So it's different for every substance, and it's also different for each state of matter that a substance can have. So what portions of the graph would specific heat values help us? Well, hopefully you said the portions of the graph where we have a specific substance, specific state of matter, and that specific state of matter is being heated, and the temperature is increasing. So the portions where the temperature is increasing are going to be 1, 3, and 5, the diagonal portions of the graph. All right, so on those portions, we're going to be able to use Q equal MC delta T, C being specific heat, which we just talked about. Specific heat can have two different units. You can either have joules per gram degree Celsius or kilojoules per gram degree Celsius. Based on what your specific heat is in, will determine what your unit for Q is. Q is the energy or the heat that you lose or gain, and Again, based on what your specific heats were in, it'll be either in joules or kilojoules. M is mass in grams. And then we already covered C, and then delta T is the temperature change, and it can be in degrees Celsius or in Kelvin. So basically, when I say delta T, you need to be thinking T final minus T initial, okay? Because that's what delta T means. All right, here's an example. So if water has a specific heat capacity of 4.184 joules per gram degree Celsius, this means it takes 4.184 joules to heat 1 gram of water by 1 degree Celsius. So how much energy would it take to heat 10 grams of water 1 degree Celsius? Well, we know that it takes 4.184 joules to heat 1 gram 1 degree Celsius. So if you had 10 grams and you wanted to heat them 1 degree Celsius, you could just use the specific heat value as a conversion factor here. So grams and degrees Celsius would cancel, and you had 10 grams, so there should be 10 times as much energy required. So 41.84 joules. Okay, now how much energy is needed to heat 30 grams, so that's a mass, right, from 10 degrees to 50. So this is the initial and this is the final. So we're going to be using our Q equal MC delta T here. Okay, delta T is T final minus T initial, so 50 minus 10 is 40, so there's delta T. M is the mass, so you got 30. C, still water, so we're still going to use 4.184. And then we just found delta T to be 40. Okay, if you multiply all those across, you will get the energy required to heat 30 grams of water by 40 degrees Celsius. And I got this. If you sig figged it, it'd be that. Okay, so 5,020 joules. All right, so when the Q is negative, it means that we are releasing heat, so that's an exothermic process. When the Q is positive, like on the last problem, means heat is absorbed, which is endothermic. Okay, so remember thinking about, going this way, you're thinking about going down, and this one you're thinking about going up the heat curve. Delta T is always going to be final minus initial temperature. So if something is getting hotter, going from 10 to 30 degrees, the delta T is going to be 30 minus 10, which is positive 20. So the heat is absorbed. So that's a endothermic. And if something is getting cooler, going from 75 to 25 degrees, the delta T is going to be 25 minus 75, so negative 50, which means heat is released. Okay? All right, so now let's look at this problem where it kind of asks us to combine some of the knowledge that we've gained. So it says we have 90 grams of hot water that was at 90 degrees Celsius, and we're going to mix it with 10 grams of cold water that's at 10 degrees Celsius. Wants us to find the final temperature once this system has reached thermal equilibrium. So we're going to set up two expressions. We're going to do hot water and cold water. Well, hot water should be losing heat, right? Because it has more, and we know that heat transfers from the highest to the lowest. All right, so you have negative Q, so make sure you throw that negative in there whenever you lose energy. The mass of the hot water was 90 grams. The C, because we're dealing with water still, is 4.184. And delta T. T final we don't know yet. That's what we're trying to find. And then minus T initial was 90. All right, now we're going to do the same thing but for cold water. So cold water is going to gain energy, so it'll have a positive Q. There were 10 grams of cold water. Specific heat is the same, 4.184. Going to be finding T final in just a second. And the initial for the cold was 10. All right, so what you want to do is you want to go ahead and move that negative over to make the Q positive. Now you have Q. Well, we know that the heat that is lost by the hot water will be gained by the cold water. So we can set these equations equal to one another. Okay, so that's what I'm going to do real quick. I'm going to just go ahead and rewrite my equations. I'm going to go ahead and change TF into X at this point. Set it equal to the cold water equation. And again, TF is X. Okay, now you're just doing a math problem. Okay, so 4.184 is on both sides, so it can cancel. Then we're going to distribute. So we got negative 90x plus 8100 equals 10x minus 100. Combine like terms, so I'm going to move 100 over here and the 90x there. So we get 8200 equals 100x. All right, and then divide by 100 to get x by itself. And the the final temperature is 82 degrees. And that was the T final. Okay?